Hi, my name is Rachel. Welcome to this advanced journey into smart contracts. Today we're going to study the chapter Smart Contract Development, Advanced. We'll go beyond basics and learn how contracts actually work under the hood. By the end, you'll understand Solidity internals, proxies, optimization tricks, and testing frameworks. Think of it like opening the hood of a car, only with blockchain machinery. Solidity internals and compilation pipeline. Solidity is the most popular smart contract language, but before running, it goes through a compilation pipeline. First, code is parsed into an abstract syntax tree, AST. Then it's converted into intermediate representation, optimized, and turned into EVM bytecode. The bytecode is what executes on Ethereum. Knowing this pipeline helps debugging, optimization, and preventing vulnerabilities. Why internals matter? Most developers stop at writing Solidity, but professionals must know how compilers transform code into bytecode. A small mistake can cause gas costs or bugs. For example, the compiler may optimize storage or inline functions, affecting behavior. By learning internals, you predict and control what's inside the EVM. This becomes crucial in audits and secure design. Storage slots and variable packing. In Ethereum, storage is like a large key-value database with 32-byte slots. Solidity assigns variables into these slots. Smaller types like uint8 or bool can be packed into one slot, saving gas. Misaligned variables waste slots and cost more gas. Developers should structure variables carefully to maximize storage efficiency. Example of variable packing. If you declare uint8a, uint8b, and uint256c, the first two fit in one slot, while c needs another. But if written uint256c, uint8a, uint8b, the small variables won't pack together, wasting space. This shows variable order matters. Efficient storage saves both gas and money. Memory versus storage versus call data contracts use three main data locations: memory, storage, and call data. Storage is permanent and expensive because it stays forever on-chain. Memory is temporary, existing only during a function call. Call data is read-only input data and cheapest. Choosing the right data location drastically changes contract efficiency. Smart developers always optimize this. Minimal proxy contracts, EIP 1167. A minimal proxy is a lightweight clone of a contract. Instead of redeploying the same code, you deploy a small proxy pointing to one logic contract. Defined in EIP 1167, it saves gas and storage. For example, thousands of ERC20s can be deployed using proxies instead of full contracts. It's like reusing a template. Why minimal proxies are useful without proxies? Deploying many contracts wastes gas. Proxies reduce costs by delegating function calls to a master logic contract. They also make upgrades easier since you update logic once. This is why DeFi protocols and NFT projects widely use proxies. They're efficient, elegant, and industry standard. Proxy upgrade patterns. Smart contracts are immutable, but upgrades are often needed. Three main patterns exist: transparent proxy, UUPS, and diamond. Each separates logic from storage differently. These patterns allow fixes, new features, and improvements without harming user funds. Proxies balance immutability with upgrade flexibility. Transparent proxy pattern. This pattern uses two contracts, proxy and implementation. Users interact with the proxy, which forwards calls to logic. Only the admin can upgrade the implementation. This prevents users from misusing upgrades. Transparent proxy is the most widely adopted pattern, especially with OpenZeppelin libraries. UUPS proxy pattern. UUPS is lighter than transparent proxy. Here, the implementation contract manages upgrades, not the proxy. This makes it cheaper and more efficient. But mistakes in upgrade logic can lock contracts permanently. Still, UUPS is preferred in many modern systems for its flexibility. Diamond pattern. The diamond pattern works for large contracts with many features. Instead of one implementation, multiple facets handle different functions. The proxy routes calls to the right facet. This modular approach allows scalability, like connecting Lego pieces. DeFi systems sometimes use this for hundreds of functions. Multi-call and batching techniques. Multi-call bundles multiple function calls into one transaction. Instead of sending 5 calls, you send one with all included. This saves gas and reduces congestion. It's widely used in DeFi dashboards and wallets to fetch balances, prices, and allowances together. Users also benefit with one-click execution. Signature-based execution, EIP 712. EIP 712 enables structured signatures for Ethereum. Instead of signing raw data, users sign typed, human-readable messages. This prevents phishing and improves clarity. A major use case is permit functions, where approvals happen with a signature instead of a transaction. This makes DeFi smoother and cheaper. Permit example. Normally, approving tokens requires 2 transactions, approve and then swap. With Permit, users sign once and the app handles both. This saves gas and reduces clicks. Many modern tokens like USDC and DAI already support EIP 2612 permits. It's a major UX improvement for DeFi apps. Optimizing contracts for gas efficiency. Gas equals money, so contracts must be optimized. Techniques include reordering storage, using call data, minimizing loops, and emitting events instead of storing data. Small changes can save thousands in gas fees. Writing efficient code shows professionalism and responsibility. Error handling and revert patterns. When contracts fail, execution must stop. Solidity provides require, assert, and revert. Require checks inputs and conditions. Assert is for internal errors and should rarely fail. Revert returns custom error messages for debugging. Good error handling ensures safety and improves user understanding. Testing frameworks. Hardhat. Hardhat is a popular contract testing framework. It lets developers write tests in JavaScript, TypeScript, fork mainnet, and debug easily. Plugins provide gas reporting, coverage, and integration with Ethers.js. Hardhat is often the go-to for professional projects. Testing frameworks. Foundry and Truffle. Foundry is newer, written in Rust, and very fast. It lets tests be written directly in Solidity, close to the contract's logic. Truffle is older, but offers migrations, testing, and deployment. Each has strengths, and serious developers learn at least 2. Testing is critical since deployed contracts can't easily change. Conclusion. We explored advanced concepts in smart contracts today. You learned about Solidity internals, variable packing, memory, proxies, batching, signatures, optimization, errors, and testing. These concepts may feel tough now, but they're essential for blockchain engineers. Mastering them makes you not just a developer, but an architect of decentralized systems. Thanks for joining this journey.